This is a Queen Mary's College video on the benzene molecule C6H6. We're going to be looking at the early ways that benzene has been represented and the shortfalls in those ideas and how more sophisticated models have been developed. So first isolated by Michael Faraday, C6H6 does suggest there's multiple bonds between the carbon atoms. So possible structures that were thought through at the time for C6H6 are shown. In fact, there was a particular favorite for the benzene molecule at the time, and that's highlighted there. Until Kekulé had his dream and revealed to him the structure for benzene, a ring of 6 carbon atoms with the alternate double single bonds there. His ideas were ridiculed, but they did move the chemistry of benzene forward.
Sodium and chlorine seem to combine with each other according to fixed ratios. It was this combining power of atoms that inspired German chemist August Kekulé to develop a system for visualizing the chemical structure of various molecules. Kekulé represented the atoms by their symbols, then added marks to indicate how they bonded with each other, like links in a chain. It was a simple yet elegant formula. Chemists now had a device for clearly illustrating the chemical structures of the molecules they were studying. There was just one problem. Benzene was the only known chemical that would not fit Kekulé's formula. Benzene's chain of carbon and hydrogen atoms required more combining power than the formula would allow.
And all these organic chemistry professors are puzzling about it and offering different explanations. And one of them, August Kekulé, sitting by the fire one evening, falls asleep and starts to dream about a snake. And if you think about a snake, what Kekulé dreams of is the snake catches its own tail. And if you think about this, maybe the thing is a ring. And that gives you an answer to the puzzle.
The 6 carbon atoms of the benzene molecule weren't linked in a chain. Like the snake, they formed a ring, each with a hydrogen atom attached, with alternating single and double bonds. Within a short time, Kekulé's insight was confirmed, and its effect was revolutionary. Chemists knew that all organic substances contained 1 or more carbon atoms in their molecules. With Kekulé's discovery, they now had the underlying formula to explain how carbon combined with other molecules to form a world of chemical compounds. The modern era of organic chemistry was born. Now, with this thing being so simple, that is to say, the snake bites its tail, why is this considered a great discovery?
Here is a recipe for new drugs, new medicines, new understanding. If you go back in time, in Dalton's day, a couple of hundred compounds. Soon it's a couple of thousand. Soon it's 10,000. Astonishing. Soon it's 100,000. Last year, 15 million new compounds were registered, all built on this simple template. This is a work of genius.
So we need to remember that Kekulé's benzene is this ring or cyclic structure with the alternate arrangement of double bonds between carbon atoms and single bonds. Not forgetting that each carbon atom has just 1 hydrogen atom bonded to it. Can we propose a name for this alkene structure of that Kekulé proposed? well done if you got cyclohexyl 1,3,5 trying. So it's an alkene, so these are of course unsaturated molecules, very reactive, and you remember the test for alkenes from last year, decolorizing bromine water very quickly. So in fact, actual benzene does not react with bromine water. So actual benzene is not an alkene. Here are some images of actual benzene. So we're going to take a look at where Kekulé's model fits in with these images and where it doesn't. Let's take a look at the bond lengths involved. We've got the carbon, the single bond carbon, bond length given there, and the double bond, and you can see that the double bond is much shorter. So Kekulé's alkene, with its alternate arrangement of double and single bonds, would not be a regular hexagon. It would have 3 long bonds and 3 short bonds. Looking at actual benzene, a perfectly planar regular hexagon shape, 120-degree bond angles, and all the bond lengths are exactly the same. Here's a representation of the ring of carbon atoms. You can see that each carbon uses 3 of the outer shell electrons to form bonds to each other and the hydrogen. That leaves 1 electron unused on each of the 6 carbon atoms. And these electrons are believed to be mobile, delocalized, free to move between several atoms. So this freedom of movement, these delocalized electrons, gives rise to the benzene ring. So the benzene ring is 6 delocalized electrons, 1 electron from each carbon. These 6 delocalized electrons are free to move within circular orbitals, 1 above and 1 below the plane of the molecule. And this freedom of movement, these delocalized electrons, brings about extra stability for the benzene molecule. The more electrons that are delocalized within a molecule, the more stable it is. So we'll revise electrophiles and nucleophiles and consider which of these attacking species will react with the benzene molecule. Here are the definitions to remind you. Let's revise the reaction between ethene and bromine. Ethene with its double bond between 2 carbons and the bromine molecule. You remember the first step is where the bromine molecule approaches very closely the double bond, and that induces a dipole. And then the electrophilic bromine, with its partial positive charge, accepts the electrons from the double bond and forms a new bond with it, and then both of the bromine atoms add on, giving you just a single product. But in fact, actual benzene doesn't undergo addition reactions, because if you try to add on an electrophile using the electrons of the ring, that would break up the ring and the delocalization would be lost. So let's take a look at an animation of this electrophile with the positive charge, symbol E. So here it is, attacking the benzene ring, new bond formed, and you can see the electrophile has added on, but we have lost the benzene ring, so the product of addition, electrophilic addition, is not stable. If we make a small change to the previous mechanism, we've got the electrophile using the double bond electrons to form the new bond. But this time we have an intermediate form that has an incomplete ring, and the change here is that the electrons associated with the carbon and the hydrogen bond are used and put back into the ring, giving us a stable product where the benzene ring is re-established, but this time we've lost the hydrogen as H+, so instead of an addition reaction which disrupts the delocalization of electrons, the substitution reaction as an alternative does not. So electrophilic substitution does give us a stable product.